for the introduction, C10. Yeah, so this is joint work with C10 and a student at Harvard. I'm going to be talking about, I think, a slightly different setting than I think most of the talks I've considered so far in this workshop, if I understand correctly, which is in the discrete diffusion setting. OK, so I'm going to skip past this slide. Although I will mention that there has been a lot of interest in not only the continuous diffusion setting, which I think most of the talks have been on in this workshop, if not all so far. Correct me if I'm wrong. But there is a lot of interest also in this notion of discrete diffusion. Right? This has in particular been useful both as an alternative way of doing language generation and also for other settings such as protein and other sort of biological applications. Also, my best guesstimate of this talk is that it should be fairly short because, to be honest, like the concepts in this talk are not that challenging in some sense. So feel free to interrupt with questions. OK, so let me just give a very brief sort of, this is there are more complexities to mass diffusion models and discrete diffusion models in general, but this is sort of a very high-level introduction to this that will suffice for our purposes. Right, so, OK, so when you're doing a diffusion model, you always have some sort of backwards process, but we're trying to do a diffusion model over a discrete space as opposed to a continuous space. And the backwards process here that we're going to consider, there's other backwards processes considered in discrete diffusions as well, but in this one we're going to consider the unmasking process. Right, so the forward process associated with this is just the one where sort of, at every time step, a random token is replaced with the sort of a special mass token, a sort of bot token, right? And the goal of a mass diffusion process is to learn to reverse this noise process. Okay? And of course, if you could do this exactly, then you would solve the sort of sampling process, right? What you would do is, of course, you just start from this, and then you would just generate real text. Okay? Now, what is the sort of backwards process? Well, there are more complicated ways of saying it, but one very basic way is to train such a mass diffusion model, or MDM for short, it is equivalent to learning how to learn these conditional marginals. Right? So what you want to do is you want to learn this function, this sort of conditional law, which is sort of, at the ith position, I want to learn the conditional marginal of sort of the ith token, conditioned on some other set of tokens as being revealed to be some z. Right? And if I've learned all these marginals perfectly, then of course I can, just by chain rule, I can perfectly reverse the reverse process and sample from my distribution. OK, so hopefully this is all fairly straightforward. So far nothing hopefully is too complicated. And of course, in practice, what you do is you try to learn this somehow using some sort of, I think often some sort of like transformer network nowadays. OK, so this is sort of the traditional sort of mass diffusion model. And of course, there are other types of diffusion models, or discrete diffusion models. There's like uniform and so on and so forth. But this is sort of what we're going to consider in this talk. OK, and the claim is that these seem to work pretty well in practice. OK, now a high-level question that we might be interested in understanding is like, why do this process, right? Like LLMs are pretty good. Auto-regressive models are very powerful. Like this sort of traditional transformer-based LLMs are very powerful. Why do we want to consider discrete diffusion? Well, I would argue one of the primary advantages of, at least potentially, of the discrete diffusion as opposed to auto-regressive models is that their inference could be parallelized. Okay, and as we all know, sort of inference time right now is scaling a bunch, right? And in principle, because sort of inference time scaling also improves quality, if we can get faster inference, maybe we can do more inference time scaling and also improve quality as well. Right, so the key sort of one bottleneck of sort of traditional autoregressive models is sort of, again, like a kind of silly statement, is that because you're doing autoregressive, doing next token prediction, it's sort of inherently sequential process. Right? You just have to generate the next token, then you have to update sort of all the, the context, and you have to update, the KV cache or whatever, and then you generate another token. Right? So it's slow at inference time. So here's sort of like a toy example. Imagine sort of I have an alphabet of zeros and ones, right? And I have an LLM that's trained on, or autoregressive model trained on predicting sort of zeros and ones. Then it learns some estimate, pretty good in practice, of the sixth token conditioned on the first 5 tokens being revealed. But in some sense, it has like no sense of what the 7th token should be. You can do sort of heuristics and maybe to guess and stuff like this. But at the heart, sort of, it really has to go one at a time. And it sort of has to recompute all these marginals one at a time. OK? Now, discrete diffusions, on the other hand, they can, at least in principle, perhaps be parallelized. Right? Like, suppose I've unmasked these tokens. So these are some random positions I've unmasked. Now, the way a discrete diffusion works is it has to learn all of these marginals, right? Because it has, what it's going to do is going to choose a random position and unmask that next position. So it needs to know somehow, it needs to have learned a good estimate of all these marginals. And in principle, suppose all these marginals are like independent. Of course, this is not the case, right? Revealing a marginal will change the other marginals. But suppose that these marginals were largely independent, then I could like reveal a bunch of them all at once, and this would have like no effect. And then instead of unmasking one token at a time, I can unmask a large number of tokens in parallel, and this could speed up inference, at least by some constant factor, if not more. Okay, so this is the basic idea. This is one, I think, sort of basic advantage potentially of these discrete diffusions.
Sorry, how do you do it all at once when you're training a scheme is one at a time?
Well, so the training scheme learns all these marginals, right? It learns the marginal of this condition on these revealed tokens. It learns so like in theory, if these are distinct, if these are independent, I could just reveal them both, and it wouldn't change anything.
But they are not.
Yeah. So this is what the talk is going to be about, like the effect of ignoring these.
And also on the auto-regressive one, you could have trained the auto-regressive model any order, right?
You could train auto-regressive.
I mean, you could train language model any order.
But that essentially becomes sort of this sort of process, right? Like if you.
That's a very simple tweak to auto-regressive training.
But then it is more or less equivalent to a mass diffusion. Yeah, but the point is that because the question is like if I have the high level point of the talk is going to be if I have access to these marginals, how much parallelization can I obtain? Yeah. Okay, so that's the basic question, right? So, and again, there's a lot of sort of intricacies of this that I'm kind of brushing aside, but one reasonable heuristic, given that sort of a mass diffusion model is supposed to learn this uniform unmasking process, or this unmasking process where, at time t I choose a random index and I unmask it. A reasonable heuristic in practice is to do the following. What you do is you fix an unmasking schedule. So this is just like S1 through Sk. Okay, so let's say there's n total tokens. So the S1, the sum of the Si is going to be n. At time t, 1 equals n, what you're going to do is from time t equals 1 up to k, you sample some subset of the tokens that haven't been revealed so far. Right, so this is kind of the trivial sort of schedule. And then what you're going to do is, for every index in this set, you're just going to sample independently from the marginals that you have at this point. Right, sort of the sort of obvious schedule. Right, exactly what I said before. Right, so I'm just going to hope that the marginals that I choose to reveal at this time step are like roughly independent. And then I'm just going to reveal them all simultaneously based on the marginals of so far. And again, this will be lossy in general because it's going to ignore correlations within the sort of time step st. Okay? But this is a reasonable heuristic, and this is what people often do in practice. And the question is sort of, how far is this distribution from like the true distribution? Right? Where the true distribution I'm going to define just to be the one where you sort of, you reveal one at a time. All right? And as a notational thing, I'm going to let new superscript S1 through Sk denote the resulting distribution. Okay, so hopefully this is all clear so far. Okay, and then so the basic question is how much can we parallelize MDM inference using these sorts of scheduling steps? And this work, what we show, is a surprisingly tight characterization of the information loss for any sort of inference schedule of this form, where I sort of denoise or I reveal SI tokens at a time, as a nice function of the underlying distribution, and in fact sort of reduce this problem to a very basic problem in univariate approximation theory, which is kind of cute. Okay, so this is the basic result. Again, I feel like it sounds complicated, but really all the results, once you have the conceptual framework sort of in place, everything is fairly straightforward actually. So hopefully more or less all the proof should be given in this talk actually. Okay, but yeah, any questions so far? Any other questions so far? Otherwise we're good. Okay, oh yeah.
Sorry, I couldn't understand what is the baseline that you want to reach. Is the two conditional distribution?
Oh, good. Yeah. So the baseline is just if I don't do any parallelization. So I'm assuming. So I guess for simplicity in this talk, I'm going to assume you've trained to, zero error. Although in the paper we also handle the sort of error in the training process. But assume that the sort of true distribution is one where I sample one token randomly at a time.
So auto-regressively?
I mean, in this case, it doesn't really matter because like you'll always get the true distribution, right? And if you have the marginals exactly, it doesn't really matter. Yeah, but the sort of true distribution is just revealing one token at a time. Yeah, and the question is, how close are you to this true distribution? Okay, yeah. Okay, cool. So the basic quantity that will be of interest is this notion called the information curve. It's a univariate function from 1 through n, and the claim is that we show that the parallelization loss is exactly characterized by the shape of this function. So this is a function that depends on the underlying distribution mu. So this is of the true distribution, the one where you reveal one token at a time. We call it z. And it's just this function. So z sub j is the expectation if I take a uniformly random subset of size j minus 1 and a random coordinate I, not in the set S, of the mutual information between xi and xs. All right, so this is the information curve. It turns out that this is a monotone function in j. So as you're increasing, this quantity is always going up. And there's maybe a slightly nicer interpretation or equivalent interpretation of this function, which is I'm going to let this quantity h sub r denote the sort of entropy of x sub s, where s is a uniform random subset of size r. Okay, this is entropy of like a random set of r coordinates of my distribution. Then a simple observation is that everything in this quantity is linear, right? So this is a definition of mutual information. And I can just push the expectations inside. And so what I get is just this quantity, just h1 plus hj minus 1 minus hj. So it's sort of up to this sort of normalizing, or this sort of universal constant, which ensures things are like nice and 0 at j equals 1. There's just a difference between how much the entropy is changing, okay, of a random subset. And our result is that the loss of information due to parallelization is exactly described by the best k-flat approximation to this curve. Okay, so let me make this slightly more formal. Here's the main result. So it's a lot of words, and I'll say the words, but really it's like the picture makes it, I think, much cleaner. So fix any like unmasking schedule S1 through Sk. Okay. What I'm going to define is the left Riemann approximation to this curve, this information curve with steps S1 through Sk. It'll become clear what this means in a second. But just think of this as like a sort of piecewise constant approximation to the to z. And the claim is that if I fix this unmasking schedule S1 through Sk, then the KL, the expected KL between the true distribution mu and the sort of unmasked distribution where I unmask with S1 through Sk, where these are random subsets of the appropriate size, is exactly given by the L1 distance between the true function and the sort of Riemann approximation. Okay, I'm not sure if this made sense, but I think hopefully the next slide will make it clear. Really, all that's happening is the following. Suppose I have this information curve, again, this monotone function from 1 through n, right? And suppose I have a step size schedule where sort of as like at the first step I reveal 4, then 5, then 2, then 2. Okay? What I do is I just take again, literally the left Riemann approximation with these step sizes, right? So I take the left Riemann approximation to this up to the first 5 steps, then the left Riemann approximation, and so on and so forth. And the claim is that the expected KL loss is exactly characterized by the sort of error of this approximation, the L1 error of this approximation. Okay. Hopefully that and that's exactly what the theorem is saying in like pictures. Hopefully now the statement is clear. Okay. If there's any questions, happy to field them. Yeah.
So do you think there's a lot of similarity with the optimal scheduling for the continuous diffusion, like where you use the exponential schedule?
There's a lot of connection between this, and I think there's some work that has explored this. There is a fundamental weird distinction, which maybe I'll discuss at the end, which is that these optimal schedules in the continuous case are for like the Gersonov upper bound. So it's not necessarily upper bound for like the true KL of the revealed thing. But the nice thing is that for like mass diffusion models, the Gersonov bound is tight, like because sort of the mask, the path is the entire process. But there's definitely a connection.
Thank you.
Yeah. Okay. So as a result of this, there are some very basic corollaries that we get, which I will say is a set of results. First of all, in this case, convexity actually goes the right way for us. So if we care about the overall law of this process, where we parallelize and we choose SI things, at every time step, then you can upper bound the KL of that by this sort of expected KL quantity. And so you actually upper bound the KL of the overall process by this L1 error as well, which is nice. And also, kind of trivially, from this characterization, we know that for this loss, at least, this expected KL difference, I mean, it's kind of trivial. But if I told you, if I only was allowed K steps, right, then the optimal schedule is the one that minimizes this loss, right? The best K flat approximation to Z, using a left Riemann approximation. Okay, so this is kind of trivial, in some sense, given our result. We have other results as well. So one unfortunate thing about this result is that this scheduler, while it is optimal, depends heavily on knowledge of this information curve, this sort of univariate quantity. But we show that this is in some sense intrinsic, that if you don't know Z, there's no sampling algorithm that can achieve sublinear sample complexity. Okay? And as a sketch, I'll try to sketch this. The basic version of this result. It's a sort of a silly, well, I shouldn't say silly, but it's a very simple counterexample instance. Although we actually do have more sophisticated results, sort of instance optimal style results as well in the paper. The basic idea is suppose your distribution is like uniform over a linear subspace of dimension L for some L which is unknown to the algorithm. The claim is that the scheduler needs to exactly hit this quantity L, otherwise it's screwed. It can't ever get good error. Right? The claim is that if you've revealed less than L coordinates, then all the marginals look completely uniform, and so you've learned nothing about what L is. But on the other hand, if you reveal more than L coordinates and you haven't hit L exactly, then you're probably out of distribution, because you're supposed to be in some linear subspace and you revealed too much, and you're no longer going to be consistent, and so you're going to get nonsense. So somehow your scheduler needs to exactly hit L. If it doesn't, then you're screwed. And we also have, again, as I mentioned, we have more general lower bounds in the paper as well. Okay, so in general, this is saying that for like arbitrary distributions, you cannot hope for at least sublinear with this sort of style of sampler. But this is kind of silly because, okay, for instance, for this instance, if I had a little bit of information, particularly if I knew L, there's a sampler that is perfect with 2 steps. I sample exactly L coordinates and I sample all the rest. Right? So what if I have like a little bit of a priori knowledge? And it turns out that the answer is, at least for this, you can do something very interesting in terms of these quantities called the total correlation and the dual total correlation, which are sort of classical things that have been studied previously in the literature. Okay, so I'm going to define what they are. So they're TC and DTC for short. They're both sort of, I would say, standard measures of how close the distribution is to being product-like, I guess, is maybe the right way of saying things. Yeah.
So when you said the iteration complexity, it's specific to this your type of algorithm where you just sample the product distribution from each S1 to Sn. It's not like
it's actually is in the paper. It's actually against sort of generic algorithms.
But I guess I actually have a result that say you can for this discrete math diffusion you can sample using square root and round.
That's a different model. That's the one where you can send off conditional queries in parallel. This one you can only query one subset, one partial assignment.
Yeah, so I guess there's the other parallel model that's been studied by like Anari et al. And folks like this.
I see. So here you allow only one.
Right.
So you allow one query. One
right. Yeah. If you only get marginal access and you can't sort of do additional stuff in parallel, then yeah, there's nothing you can do in some sense.
So I'm kind of confused about your model of sequential complexity. Like parallel sampling. And is this like in each iteration you allow only one marginal query? You not allow parallel.
Well, you get all the marginals given condition like on things that are revealed.
Okay, so
but if you want to like get marginals of like different things that are of like different revealed things, then you'd have to pay additional cost. That's not for free.
I see. So you just go and get one vector of all things.
Yeah. So it's like if I only have like one GPU running this stuff, or one core running, yeah. But yeah, okay. Okay, but yeah, so what are these measures, TC and DTC? I mean, TC I think is very standard. I mean, this is literally sort of the KL between like the product version of the distribution and the sort of the true distribution, but it's the sum of the entropies of each coordinate minus the joint entropy. So for instance, if the distribution is product, then this is 0. So it's a very natural measure. Dual total correlation is a little bit weirder maybe. It's sort of the overall joint entropy minus the sum of the entropies of like each coordinate conditioned on everything else. Right? But it's still some sort of measure of sort of how close you are to being product. And intuitively, these things exactly measure. So again, TC literally says your KL is close to some product distribution. And it turns out that what small DTC says is that your distribution is close to some mixture of products. So this is a result by Austin. Okay? And what our final set of results say is that it is possible to sample to error epsilon, where this is in the sort of expected KL or in KL error, using k steps where k is the minimum of TC comma DTC times log n over epsilon. So in particular, if either of these quantities turn out to be sublinear, you're able to get sublinear sample complexity, or query complexity, or step complexity for this problem. And so the nice thing is that, at least in practice, this would reduce the problem to a single hyperparameter sweep. You just sort of sweep over what your guess of DTC or TC would be. Okay? And this result is also, turns out to be, it follows almost exactly from our exact characterization. There's a really nice picture involved, because these quantities, perhaps unsurprisingly, are very closely related to this information curve. In particular, you have the following, that the TC is the sum of the ZIs. I guess I should be bolded, my bad. And the DTC is n times Zn minus the sum of the ZIs. In other words, it's n times Zn minus the TC. And so there's a really nice picture. What I can do is I can draw this graph where I imagine, okay, I'm drawing it continuously, but I'm drawing it from 1 to n. And I have this box, right, that goes from 0 to Zn. Now, the information curve is some monotone function on this box. And what these expressions are saying is that TC is the integral of this graph, of this function. And DTC is the rest of the area of the box. Okay? And from this, it might be unsurprising that sort of these are related. Right? Because the claim is that sort of if this box is small, then either TC, or like if either of these quantities are small, then you can hope for a good piecewise approximation to this information curve. And indeed, this is true. In fact, this is a classical thing. This is actually known from like the statistics literature in like the 80s. It's kind of cute. So here's a, formally speaking, so what I let is I define Qi to be Zi over Tc. So note that the Tc is the sum of the Zi's. So the Qi is a now probability distribution over 1 through n. Okay, and it's monotone because the Zi's are monotone. Then, yeah, again, this is sort of implicit in this sort of called Berger approximation from the 80s, that any monotone function can be approximated to total variation distance, which is equivalent to L1 distance, up to error epsilon, with log n over epsilon many pieces. And this sort of tight, like you need this many pieces as well. Okay? And if you just like plug in this result to Qi and recall that what we care about is the error of the best k-flat approximation, then this immediately says that you just take this approximation and you get a scheduler that takes Tc log n over epsilon steps. All right? Does that make sense? And for completeness, we actually do this properly in the paper because Berger's approximation is sort of implicit in this sort of statistics literature. But the key idea, the key point is that, again, if the total correlation is sublinear, we can achieve sublinear sampling with actually a fixed schedule that only depends on Tc. And what you do is you take some sort of exponentially decreasing step size. So what you do is initially you sample many, many things in parallel, and then you get more and more conservative as you go on. Okay, this is how you get this sort of schedule. And there's a similar schedule for DTC. That there exists a similar result where I replace the TC with DTC. Okay, in this case, the schedule is perhaps unsurprisingly exactly the dual to the TC schedule. What you do is you start out very sort of conservative, and you get more and more aggressive as you go on. And actually, this is close to the things that people actually do in practice. Okay? And again, this just follows almost directly from our characterization. I should mention that there has been a lot of interest in this, and there has been prior work on this. In particular, there's a paper by Li and Kai that showed that the expected KL loss can be upper bounded by slightly worse quantity. So instead of min, of TC and DTC, they get the sum or the max of the TC and DTC. There's also a result that's a corollary of these Austin's results on on characterizing DTC, where you get some result which is somewhat incomparable. It's like the geometric mean of n and DTC. Okay, so in some regimes, this could be better, but. And I want to say, finally, there was a concurrent work of Lavenant and Zanella. I don't know how to pronounce them. Apologies. But it also derived the same connection. Although I don't think it didn't quite get into all these sort of structural things. It was more interested in sort of like some asymptotic behavior. But it derived the same connection to the information curve. And also, I think, considered, yeah. OK. So I have some time. So I want to just show, again, I feel a little bit silly calling this a proof of a main result. This is really just a calculation. So I just want to show this because even though it's sort of a simple calculation, maybe perhaps it's still a little bit enlightening. And I want to mention, even though I feel like sort of everything follows very straightforwardly after you have this, I feel like really this connection to the information curve is a really nice contribution because everything is like super. The picture of this problem becomes super clean once you realize that the information curve is like the right quantity to consider. OK, so let me just do this calculation really quickly, hopefully. OK, so I'm going to focus on a step I. Right? So at step I, I've already revealed some tokens. So I'm going to let T sub I denote the set of coordinates already sampled. Then, by definition, the sort of for a fixed S1 through Sk, the KL between mu and nu, superscript S1 through Sk, is the sum of the conditional KLs, where this mu tensor just means I sample Si, all the coordinates in Si simultaneously, from the product distribution, where this is the true distribution of the Xi's. OK? Now, if I fix a conditioning, like if I fix a value of this, then this is a very simple expression. So for a fixed set Si and a fixed set of revealed things, literal xti, this KL, I mean, this is literally the KL between the true distribution and the product version that matches the marginals. And if you stare at this for a second, this is literally sort of the total correlation of this function, of this sort of conditional distribution. Right? So it's the sum of the entropies of the Xi's that I'm revealing minus the joint entropy. OK? And then so recall there was an expectation over on the outside here. So I need to expect over little xt. And so when I do this, this just becomes the sum of the joint, the conditional entropy. OK, but this has a nice expression. I just stare at the definition of conditional entropy. And I get, this is the entropy of xti union j minus xti. And similarly, this is x of si union ti, x of ti. OK? And the final observation is that there is an overall expectation on the outside of everything, where I expect over all the sets. Right? And now everything is linear. Right? So I can just bring this expectation inside. And then marginally speaking, this is just a random set of size, size of ti plus 1. This is just a completely random set of size of ti, and so on and so forth. Right? And so, there's supposed to be, whatever. So if I stare at this, right, so this is, the number of things that I've revealed so far is quantity capital Ni from the Riemann approximation. This quantity is just, Ni, or the expectation of this is h of Ni, and so on and so forth. And so, so this first term, right, I just get Si copies of this sort of difference, because this expectation is, yeah. And this term is just the entropy of a random set of size, this quantity, versus an entropy of a random set of this quantity. So I just get this quantity, and if you just stare at this quantity, up to this factor of h1 that's no longer there, right? The Zi information curve is literally the difference between, hi and hi minus 1. So this is literally this quantity, the entropy, the information curve at Ni. And similarly, this, I can write this as a sum of these, because this will telescope. And there's these h1s that are supposed to be hanging around, but they cancel because there's same number of terms on both sides. And OK, I kind of guess what these indices are, but if these indices are wrong, then I'm off by 1. But same idea. But the point is that this is literally, this is the integral of the information curve from these 2 points. And this is what happens if I take the left Riemann approximation. Right? So this is literally the error of the left Riemann approximation. So that's the entire proof. So hopefully that made sense. It's not like a particularly deep calculation, I would say. It's just that like once you write down the definitions of everything and you just like take the expectations inside, everything becomes marginally uniform. Okay? So that's pretty much all the technical content that I wanted to say. I think there's a lot of interesting future directions still to be explored. I think one empirical direction is like, can we implement these schedules in practice or understand sort of the effect of TC and DTC in practice? But there's also really interesting questions on the more sort of other aspects. So there are other sort of unmasking schedules that people do. So for instance, CTN has a very nice paper, and I think several people in this workshop have these nice papers on sort of high confidence unmasking. If there's some notion that you can do sort of high confidence, like a theory for high confidence unmasking, or anything like that, that'd be very interesting. There's also very interesting work on sort of understanding empirically, remasking seems to be very useful. If I find that I've made a mistake somehow, you can sort of remask and try again. And so far, the theory does not accommodate either of these sorts of like additional heuristics. It'd be very nice. It'd be very interesting to understand these things. And beyond MDMs, there's also very interesting questions. So I guess I mentioned some of these. There's also interesting settings, other settings like continuous diffusions, where maybe you can get these sorts of similar sort of tight characterizations. But there's these issues here, as I mentioned before, of like the Gersonov bound not being quite tight. And I guess, yeah, I mentioned also this sort of like high confidence questions. Like, can this sort of theory guide a different way of thinking about how to choose unmasking positions? Because in practice, it seems like sort of where you choose the token position seems to really matter. Like this high confidence thing makes a big difference. You can also do block auto-regressive, where you sort of do parallel, but only in like small blocks, and everything else is auto-regressive. This also seems to help in practice, but sort of none of the theory currently accommodates for these other kinds of schedules. So the question is, can you port these sorts of bounds to get insights into these more complex sort of schedules? Okay. Yeah, that's pretty much all I had to say. So yeah, thanks.
Could other Riemann approximations correspond to other strategies?
It's a good question. I mean, it seems like if you have other strategies, you get like you don't get a univariate quantity anymore, because like the univariateness really came from the fact that you could expect over sort of like only the size of the subset is the thing that mattered. It seems like for these other strategies, you get some much more complicated, high dimensional object. So it's like less clear how to like think about those, I guess. Yeah.
So I was thinking about how diffusion models for images can just create the whole pixel together. Also, there is this dependency between pixels, and can we use this theory to basically bound the number of inference step or backward step in diffusion model is?
Yeah, I guess this is one of the like mysteries. I don't know. Yeah, it's like one of the weird things between discrete and continuous diffusions. As you said, in continuous diffusions, you can get away with like much fewer, like 4 steps, or like 10 steps or whatever. Even with like fairly basic sort of models, even if you don't do like normalizing flows or these like fancy tricks. But for like discrete diffusions, you really have like the kind of speed of sort of like that you can expect in practice are like 4x. So you can like unmask 4 tokens at a time, and even then you get like weird degeneracies. So there are some like differences. To answer your question, I guess there is a theory that, and I think this was done in some other work, that predicts you can sort of there's a similar quantity that bounds some sort of notion of KL difference, but it's like the Gersonov upper bound typically, and the bound you get is some sort of like lower bound on that sort of error, or sorry, upper bound on that error. But that's no longer tight because, or it's not as tight. Or here we have an exact characterization. But there you can only get an upper bound for the Gersonov error. If that makes sense. Yeah.
You have these result for the sort of two different schedules you get based on optimizing the like total correlation or
Yeah.
this like total correlation? Do you have like a intuitive picture of like why for the one case like you unmask a lot to start and then it decays down and it's the opposite for the other one? Like is there
I guess it's like literally the shape of the information curve. Like in one case, like if TC is going to dominate, then that means the integral is small, so the TC looks convex, this information curve looks convex. And so that's saying sort of like most of the information is like sort of near the end. And then you need to be really careful there, but sort of you can be pretty aggressive. But otherwise, it's going to look sort of more concave.
okay, makes sense.
And then, you know, sort of that's saying sort of, yeah, the opposite. So if you had to be really careful, a lot of information is happening over here, and then near the end, you know, whatever. That's sort of the high-level geometric intuition, yeah.
So in practice, do you typically estimate?
So in practice, people do not do these schedules. We've been looking into them. They offer some improvement over. So the standard schedules for these things are like these cosine schedules. They're actually pretty similar to sort of learned schedules actually. So I guess people have found sort of like some of the information curves we've like plotted are actually they have a sort of nice shape. But yeah, if you wanted to use these in practice, in theory you would have to estimate these quantities, but I guess in practice you would likely just do a hyperparameter sweep, kind of.
But in that sense, also determining whether I need to start faster or slower, like depending on.
Yeah, correct. So I guess you'd have to like just empirically pick one. Yeah. Unfortunately, yeah, you do. There are two different schedules, and there's some sense in which sort of. I mean, our bounds are in some sense adaptive to TC and DTC, but yeah, the schedules are sort of. They're not like super compatible. That's true. Yeah, they're not compatible.
But in practice,
Yeah, in practice, all the curves are concave. Yeah. Yeah.
So based on your work, do you have any insight on why masking is typically a better noise process than random tokens?
I think this is
it's not related perhaps, but I'm curious what you think about that.
Well, I'm not entirely convinced it is better. I mean, like I know DeepMind, for
In
instance,
practice.
DeepMind uses uniform, for instance. So it's like different applications. I guess the nice thing theoretically about the unmasking process is that the KL computations are very easy, because whereas in uniform, it's like again you only get some sort of like Kirchhoff upper bound. But I think it's not settled whether or not which one's like strictly better than the other. Yeah.
Related, how does the schedule change in the uniform case?
I don't think our theory has any predictions for the uniform. I mean, there's like a different notion of an information curve you can derive. You get some sort of upper bound, and you can make schedules depending on this. I actually don't know what they use in practice for uniform. I assume probably just cosine as well. But yeah.
Sorry, this is a very embarrassing task. But I missed it. So did you have an assumption that your score is perfect?
Yeah. So I presented this assuming you have perfect score information. In our paper, we also derive, the bounds if you have, L2 accurate score estimation. But for simplicity, I guess I assume necessarily you have perfect scores here.
But the result remains the same.
Up to additive term that depends on the error.
Okay. Because so when we were analyzing the error of continuous diffusion with the analysis of the training as well. We discovered that if your training was very accurate, and then like Yang-Song's exponential schedule is better than the polynomial schedule of EDM, but typically you have some score error, and then EDM actually became better. So I think the optimal schedule in a continuous situation actually depends on like how all the error terms balance out with each other.
Oh, interesting. I think we did not look into this very carefully, but maybe that's worth.
But maybe you assume like epsilon small.
Yeah, we just assume epsilon approximate errors are everywhere. So, but yeah, if you have like non-uniform errors in training, then sure, that probably would yield different results. But I guess we didn't look into this.
I see. Thank you.